Yeah, one of the more common problems that you run into on rotating machinery today is a thing we refer to as resonance. Basically, every object and every element of a machine has its own natural frequency based on its mass and stiffness. For example, if you just consider this upper bearing of this particular structure right here, it has a very, very low stiffness in the horizontal direction, hence it has a very, very low natural frequency or resonant frequency. Vertically, it's considerably stiffer, and that just simply means it has a different vertical natural frequency. In the axial direction, we have a little bit different stiffness there, so again, we've got a different natural frequency in the axial direction. I'm going to start this up to demonstrate resonance, and essentially all resonance is a situation where you have an exciting force frequency, perhaps an unbalance, cavitation problem, hydraulic pulsation problem, and that happens to occur at the same frequency as an element natural frequency. What I'm going to do here is simply slow down this motor demonstrator. I'm going to reduce its exciting force frequency, and as you'll see, we'll reach a certain point where the vibration will be tremendously amplified. I think it's obvious that what we've done here is reach a point where the vibration is extremely high. It's much, much higher than it was at any other operating speed. And again, all we've done here is to simply adjust the exciting force frequency to make it equal to the natural frequency of this particular element. Again, this is resonance. One of the things that you'll note, this is a structural resonance, and note that the vibration is extremely directional. It's almost entirely horizontal. And this is one of the things that we look for in doing a vibration analysis to get indications of possible resonance problems. Right here, we're probably looking at almost a quarter of an inch peak-to-peak motion in the horizontal direction. Relative to that, in the vertical and the axial directions, you have very, very little vibration. One of the other things that makes resonance such a common problem is that every element in the system has its own natural frequencies, but it doesn't have just one. I want to now show you multiple modes of resonance. As we mentioned, one of the reasons that resonance is such a very, very common problem is that every element of a machine or machine system, including the base, the foundation, the bearings, the piping, and so forth, has different degrees of mass and stiffness, hence different natural frequencies. However, you can take any individual element of a system and it will have not just one natural frequency, it'll actually have essentially an infinite number of possible natural frequencies. And that's what we want to show you here with this very simple demonstration. What we have here is a variable speed motor. It's a DC SCR drive motor. And to create an exciting force, what we've done here is simply drilled and tapped a screw off-center or eccentric so that as this rotates, it produces a 1 times RPM excitation. Now, I want you to notice that the amount of eccentricity here is approximately 1/2 inch, giving us a total peak-to-peak eccentricity, exciting force, if you will, of approximately 1 inch. I'm going to start off here, and we'll bring this thing bring it up in speed slowly so you can see what's happening. As we start off, we are now operating at a frequency well below the natural frequency of this particular spring mass system. And as you can see, the amplitude essentially is approximately 1 inch peak to peak here, and then just progressively drops off to 0 amplitude at the other end. Let's continue to bring this up in speed and just see what happens. As you can see, we reach a certain speed where the system, in this case the rubber band, shows a very marked increase in vibration out here in the center portion. If we tune that just right, we can get almost 6 to 8 inches of deflection out there in the middle. This is the first bending mode of resonance of that particular system. I'm going to continue to increase the rotating speed, the exciting force frequency, and as you'll note, we reach another rotating speed or frequency. This is referred to as the second bending mode of resonance. And basically what this system has done is it's split itself now into 2 separate spring mass systems, separated at this point in the center, referred to as a nodal point. All I'm doing is simply preventing the energy from getting from one spring mass system to the other spring mass system. That is the second bending mode of resonance. Again, you'll notice that we have quite an extensive amplification of the exciting force amplitude here. I'm going to continue to increase the rotating speed. Now, we have the exciting force frequency coincident with what is called the third bending mode of resonance. And again, you'll see that the system has broken itself now up into 3 separate spring mass systems, again separated by these points of minimal vibration. Those are referred to as nodal points. If you identify a problem as resonance, obviously the question is, well, how am I going to solve that problem? The natural frequency of any system can be easily changed by either changing the mass or the stiffness of the system. Generally, a change in stiffness is the easiest correction to make. However, let's see what happens if I happen to make a stiffness change right here at the nodal point. As you can see, even a very significant stiffness change at this point really produces very, very little reduction in the vibration. However, let's see what happens if I make a change in stiffness at a point of high vibration, referred to in this case as an antinode. You can see even a moderate stiffness change there produces very, very drastic results. What we're indicating here is if you do anticipate making structural modifications or changing the stiffness of the system, it's very, very important to take vibration measurements along the system to find out where these nodal points are so that you can avoid making modifications at those locations. This is the third bending mode of resonance. Let's continue to bring this on up in speed. Now we've reached an exciting force frequency. We are exciting now the fourth bending mode of resonance. And let's assume that this was a section of piping, perhaps. It's very, very common when you install your piping support hangers that you would install those at uniformly spaced distances. And this is something that you may want to avoid. You can see that these distances between nodal points are in fact uniform. When you install your piping and the support hangers, what would be preferable is to space your supports at non-uniform distances, perhaps 13 feet, 9 feet, 11 feet, and so forth, so you avoid the possibility of sending that piping into a standing resonant mode similar to what we're demonstrating here. There's the fourth bending mode, continuing to bring it on up in speed. Now we have 5. Continuing to increase in speed, 6, and so forth. And again, any element will have essentially an infinite number of these possible natural frequencies.